scientists remain unsure about what dark energy and dark matter actually are.
The European Space Agency's Euclid Space Telescope was launched for a 6-year mission to shed light on dark energy and dark matter and chart the largest ever map of the universe.
The galaxy is swimming with dark matter, as far as we can tell, but it interacts very weakly with this matter. So we're looking for the direct detection of it. It's 5 times as much dark matter than is normal matter. And the number is 25% of the universe. So roughly speaking, about 5% of the universe is normal matter, and about 70 is dark energy.
The James Webb Telescope is a powerful time machine with infrared vision that is peering back over 13.5 billion years to see the first stars and galaxies forming out of the darkness of the early universe. The unveiling of 6 ancient galaxies more developed than the Milky Way earlier has launched a fresh epoch in our comprehension of the cosmos's evolution. Existing in an epoch just a few 100 million years after the Big Bang, their advanced development challenges existing models of galaxy formation and evolution. The most intriguing question that these findings raised was how these galaxies could have developed such complex structures in a relatively short period of time. Theories of galaxy formation suggest that galaxies gradually grow by accumulating gas and smaller galaxies over billions of years. However, the maturity of these galaxies hints at a faster or alternative evolutionary path, potentially involving unknown mechanisms or conditions in the early universe.
So that the Webb is capturing light that's been travelling for over 13 billion years, and it can see the formation of the first galaxies. It's essentially looking all the way back to very close to the beginning of time. And that's very important because we're not entirely sure exactly how those first galaxies formed. But the universe has been expanding, and so the light has been stretching. And so for the most distant galaxies, we're looking back in time almost to the Big Bang. Hubble was not sensitive to that light.
The JWST is also able to study the properties of the cosmic microwave background radiation, which is the radiation left over from the Big Bang.
There's something called the cosmic microwave background radiation, which is light that was emitted in the universe, and it's a very precise number. It's 380,000 years after the Big Bang, which is not very long at all. Right? The universe is 13.8 billion years old. So we can see that. It's microwaves because it's been stretched so much by the expansion of the universe. Going back, the problem with light is that in those earliest times, the universe was so hot and so dense that light couldn't travel through it. So it was opaque. So you can't use light to go back earlier than that. But what we can potentially do, not yet, we're not good enough yet, but the technology we use to detect colliding black holes, and that technology possibly could allow us to probe right back to this thing, the Big Bang.
By studying the CMB, scientists can gain insights into the nature of dark matter and dark energy, which are 2 of the biggest mysteries in astrophysics. Our universe doesn't make sense if we account only for the matter and energy that we can see, measure, or detect.
So we look out into the universe and we see that there's a lot of stuff there that's interacting gravitationally, but is not interacting strongly with the matter out of which we are made and the stars are made. It's almost certain that that's some form of particle that fits beautifully. And we see lots of different observations of the way galaxies rotate and interact. And even that oldest light in the universe, we see the signature of that stuff in that light as well. So we think there's some other particle out there. The galaxy is swimming with dark matter, as far as we can tell, but it interacts very weakly with this matter. So we're looking for the direct detection of it. It's 5 times as much dark matter than is normal matter. And the number is 25% of the universe. So roughly speaking, about 5% of the universe is normal matter, and about 70 is dark energy. So Einstein's theory, which works spectacularly well, says that if you put stuff into the universe and it warps and deforms and stretches, and it very precisely tells you, given the stuff that you put in it, how much does it stretch and how does it stretch? And the measurement we have is how it's stretching. The thing we observe is how the universe is expanding and how that expansion rate is changing and how it's changed over time. So we have very precise measurements of that. So then we can use the theory to tell us what's in it, given that we know how it's responding to that stuff. And that's how we discovered dark energy So we notice that the universe's expansion rate is increasing. So the universe is accelerating in its expansion, which is exactly the opposite of what we thought. Now, this is in the 1990s that we discovered that. So we can work out what sort of stuff and how much of that stuff you need to put in the universe to make that happen. And that's where we get these numbers from.
But how do you study something that can't be seen? Europe's new Euclid telescope that launched may have just the solution.
The European Space Agency's Euclid Space Telescope was launched for a 6-year mission to shed light on dark energy and dark matter and chart the largest ever map of the universe.
The telescope, fitted with sensors capable of detecting visible and infrared light, will join the famed James Webb Space Telescope at Lagrange Point 2. In this region, the gravitational forces of the planet and the Sun are equal, keeping the spacecraft in a stable location relative to Earth. Here, shielded from the glare of the star at the center of our solar system, Euclid will explore the evolution of the dark universe. It will make a 3D map of the universe by observing billions of galaxies out to 10 billion light-years across more than a third of the sky. While dark energy accelerates the expansion of the universe and dark matter governs the growth of cosmic structures, scientists remain unsure about what dark energy and dark matter actually are. By observing the universe evolving over the past 10 billion years, Euclid will reveal how it has expanded and how structure has formed over cosmic history. And from this, astronomers can infer the properties of dark energy, dark matter, and gravity to reveal more about their precise nature. Given the current gaps in our understanding of dark matter, particularly with its theoretical inconsistencies and the absence of direct evidence supporting any candidate particles, it's definitely worthwhile to entertain other explanations. In fact, Neil deGrasse Tyson has ventured to offer a unique perspective on the issue. Tyson postulates that what we consider dark matter could actually be ordinary matter, but from an entirely different universe. This idea suggests a scenario where our universe may coexist with parallel universes, and the elusive dark matter we've been trying to detect may simply be the interactions or effects of matter in these neighboring realities.
If you have multiple universes, it turns out gravity can spill out of one universe and be felt by another. And if we have another universe adjacent to ours, it could be that these sites where we see extra gravity is ordinary gravity in a parallel universe. And here we are looking at it mysteriously, like, what is this? It's like the blind man touching the elephant. I don't know what this whole thing is, but here I can describe this part of it. And you can't see the whole elephant. Maybe the elephant is ordinary gravity in another universe and we're feeling it and we're making stuff up just to account for it.
This theory, while highly speculative, underscores the importance of continuing our explorations and investigations into the mystery of dark matter. As we strive for a better understanding, we must remain open to a wide range of possibilities, however extraordinary they may seem. Adding to the discourse of theoretical alternatives, Brian Cox has shared intriguing insights on the concept of eternal inflation. This theory proposes that our universe is just one pocket within a vast, ever-inflating multiverse. Each pocket universe could have different physical properties and laws. In the context of dark matter, it's conceivable that what we observe might be a feature or effect of this broader cosmic landscape.
If you look at the galaxies, they're in sort of flows and rivers of galaxies that cross the sky in a pattern called the cosmic web. And inflation predicted that before it was seen, actually. So it's an astonishing idea. That theory has a kind of an extension called eternal inflation, which is that the inflation essentially goes on forever. And it just stops in little patches. So you imagine this, the fabric of the universe, space-time, stretch, stretch, stretch. And then it slows down and stops in little patches. And each one of those patches is basically a Big Bang and a universe, of which ours is one. So you end up with this sort of picture of an infinite fractal universe of basically an infinite number of Big Bangs. And that's called the inflationary multiverse.
While the dark matter hypothesis remains open to exploration due to its imperfections and the lack of direct evidence for any candidate particles, there are multiple scientific projects underway aiming to delve deeper into these cosmic mysteries. The Euclid mission is not alone in this pursuit. For instance, the Roman Space Telescope, an innovative observatory under NASA's banner, is gearing up to confront the enigmas of dark energy and dark matter head-on. This mission is designed not only to shed light on these elusive aspects of our universe, but also to hunt for and capture images of exoplanets, advancing our understanding of these distant worlds. Beyond these investigations, the Roman Space Telescope will dive into a plethora of topics within infrared astrophysics. So, while we continue to grapple with the complexities of dark matter and dark energy theories, the scientific community is making strides, employing multiple missions and observatories like Euclid and the Roman Space Telescope to illuminate these hidden facets of our universe.
And to make sure you don't miss out on anything mind-blowing happening in our universe by subscribing. Thanks for watching.